In this lesson, we're going to discuss the normal distribution. And in your previous video, you saw the 68, 95, 99.7 rule, which you can see here is actually just an approximation. It's not exactly those whole numbers, but for most purposes, estimating to 68, 95, 99.7 is going to be good enough for us. Your textbook calls it the empirical rule. You can refer to it as either. So our first goal here is to use our 68, 95, 99, 7 rule to first estimate the proportion of values in a specified interval, or estimate the value that corresponds to a given percentile in a normal model. So here's one example of a normal model. You can see that it's symmetric and unimodal, and we discussed that a normal model has two parameters. It has a mean and a standard deviation. So notice that I called these parameters. This is mu, the mean, and this is sigma, the standard deviation. Okay? Because we are talking about a population, we refer to these as parameters. If we were talking about a sample, we would call them statistics. So I will put that this is the mean and this is the standard deviation. So all normal models, when you write them, immediately I want you to write next to it a capital N, and then in parentheses you put your mean first and your standard deviation second. We will later on look at the normal model for all z-scores, and we already saw that all z-scores have a mean of 0 and a standard deviation of 1. So this ends up being our standardized normal model. Okay? All right, but let's just talk about a normal model first. So the mean is in the center, and it's all of your values are closely stacked to that mean. And if it's a normal distribution, within one standard deviation on both the left and the right, you have 68% of your data. And again, that's approximately goes to further decimal points. 2 standard deviations away is 95% of your data. And 3 standard deviations away, look at this, is 99.7. This is another reason why we say that something that's 2 standard deviations away from the mean is an outlier. It's very unusual. Because 95% of your data, if it's a normal distribution, is going to be within 2 standard deviations. So some other things that were highlighted in the previous video is that this is a density curve. And the exact shape of it, like how tall it is or how spread out it is, will be controlled by the size of the standard deviation. And the animated video you just watched did a nice job with that. 2 things I want to also mention is this density curve will never touch the x-axis, okay? It gets really, really, really close, but it never, ever does. And I'm unsure if I said already, but the area beneath this curve is always equal to 1. All right, so this normal distribution will become your friend in this course. We will use it all the time. So let's explore this first example. The Environmental Protection Agency, or EPA, fuel economy estimates for automobile models tested recently predicted a mean of 24.8 and a standard deviation of 6.2 miles per gallon for highway driving. Assume that a normal model can be applied. And then we're told to draw the model for the auto fuel economy, clearly label it, and show what the empirical rule predicts. So the very first thing that I'm going to do is I'm going to list a capital N next to my normal model here, and I'm going to put my mean and my standard deviation. So my mean is 24.8, and my standard deviation is 6.2. So this one's my mean, and this one's my standard deviation. And since now that I am specifically told that a normal model can be applied, I'm going to start labeling my normal model. So I've started this already. Notice the tick marks that I've written. Okay, so this first one, this is my mean, and I'm going to label this as 28.4. And now what I'm going to do is I'm going to add 1 standard deviation onto the mean, and I will continue to add. So 37.2, and 3 standard deviations away would be 43.4 miles per gallon. Now I'm also going to subtract standard deviations to the left of the mean, so this would be 18.6. If I subtract 6.2 more, I get 12.4, and then 6.2. I'm supposed to label what the empirical rule shows. So 1 standard deviation on either side of the mean contains 68% of all the automobiles tested. So 2 standard deviations on either side of the mean would contain 95%. And then 3 standard deviations away, so I'm going to put a line all the way, will contain 99.7% of all automobiles. It's also a good idea to label your normal model with a title. Now I'm going to use that normal model we just drew to answer some questions. So it says, in what interval would you expect the central 68% of autos to be found? Well, it's really easy to see here that that falls between 18.6 to 31 miles per gallon. Okay, so that's saying 68% of the vehicles are getting between those two values. What percent of autos should get more than 31? So here's 31, so more than 31 would be the proportion of vehicles in this part of your density curve. So altogether, we know that the area is 1 or 100%. So if I took 100% minus, well, what percent is contained up to 31? And there's probably a couple of ways you could do this, but my brain says, okay, so the mean is splitting right down the middle. So the mean would be 50% to the left, and then there would be another 34% right here. Where did I get 34? Because half of 68 would be 34, 1 standard deviation. So I could say 100 minus the 50 plus 34%. Or which would be the same as 100% minus 84%. And there's probably another way you can look at that picture and come up with the same answer, but I would expect 16% of automobiles to get a higher than 31 miles per gallon fuel economy. In letter D, we're asked about what percent of cars should get between 31 and 37.2 miles per gallon. So what we are going to do here is we're finding the area in 1 standard deviation. So ultimately, we want to know this region. And there's probably a couple ways you can do this again. So what I just did is I drew a vertical line because the normal model is symmetric, and I know 50% is to the left and 50% is to the right. So I just need that yellow shaded region. So I'm going to actually use a little bit of subtraction. So this region right here that I'm doing in gray, I'm going to kind of use this. So I know that the area 2 standard deviations to the right would be 47.5% of my data, 47.5%. But I want to get rid of the gray region right there. And I know because that's 1 standard deviation away, it would be 34%. So if I just take away 34%, that leaves me with 13.5% is between 31 and 37.2. Okay, a couple other ways you could get that same number, I'm sure. Part E, describe the gas mileage of the worst 2.5% of all cars. Once you've done enough of these problems, when you see 2.5%, that's going to kind of jump out at you. And here's what I recognize, okay? So 95%, what's missing from 100? There's 5% left over. So that means there's 2.5% on the left and 2.5% on the right in this interval, and this direction would be your other 2.5%. So it has to be the left side because it says describe the worst gas mileage. So it would be less than 12.4 miles per gallon, or the cars would get less than 12.4 miles per gallon.
Part F asks us, what would you consider to be unusually high and unusually low? Well, since anything beyond 2 standard deviations is unusual, an auto getting less than 12.4 miles per gallon, or on the upper tail, greater than 37.2 miles per gallon is unusual. Okay. Our last question about this normal distribution would be, what percent of autos get less than 35 miles per gallon? Well, this one's a little different. So where would 35 be? Well, 35 is going to be somewhere about right there. So less than that would be the region to the left, clearly. But our 68, 95, 99.7 rule won't help. So we need another strategy. And fortunately, we have one. We're going to be using Table A. But you're going to see how to do this in the next video.